So we're going to carry on with the inverse function theorem. We spent, remember last class, building up lots of intuition about what we thought we could prove, and we wrote down a conjecture. I'm going to be so bold as to write it down with the name theorem today, and then we'll prove it and make sure it is really a theorem. So this is the inverse function theorem. Okay, so let me just state it word for word what we wrote down at the end of last class, and then we will dig in and talk some more. So we have a transformation that is square. It goes from Rn to Rn. It is continuously differentiable. On some open set. Okay, so the Jacobian exists, and the Jacobian is going to be invertible on this set. So the determinant, the Jacobian is non-zero. Okay, now we pick a point, any point in our set. What did we argue last class? We argued that from here we probably cannot conclude that our transformation is invertible, but we're hoping that it's maybe locally invertible, that if I pick any point in this set, I can build some little neighborhood around the point on which my function is invertible if I only restrict to that neighborhood. So we said, we think there exists some open neighborhood okay, which I'll call n of x naught, on which f is regular. Okay, and regular encompassed this idea of being invertible. Okay, then we said beyond that, our open set here, which takes up some volume, maps onto another open set that also takes up some volume. That becomes important for proving a lot of these properties. Actually, this is the part, although it looks like a technical detail, that we're going to spend most of our time on probably today. Okay, so f of n is open, and we can define this local inverse. And this local inverse is basically as nice as our original transformation. It's also continuously differentiable. On its domain. Its domain is f of n. And of course, G takes us back to the original set n. And we could write down an expression for the Jacobian. So it was just the inverse of our original Jacobian. Okay, so it's a lot to write, but this is what we kind of convinced ourselves last time might be a reasonable thing to take on. So there's basically going to be three steps to our proof, three lemmas that we're going to prove, and they're going to together give us this result. Okay, so here are our three results. Try a different pen. Okay, so this is going to be our plan. Okay, first of all, we're going to show that an open set gets mapped onto an open set. Okay, so this is, a bit of a technical statement. But again, it would be important for filling in the rest of the proof. So this is This part will probably be the hardest part to prove, the one where we'll have to kind of think most carefully, but it will give us most of the rest of the results, actually. Okay, so we'll do this. Then we'll say that we can find a neighborhood of x naught on which f is regular. All right, that part, it turns out, will be surprisingly easy to prove. And then finally, we want to say something about the Jacobians. Okay, so our last step will be to relate the Jacobian of G to the Jacobian of F. And that will more or less come down to how we usually work out Jacobians, is we use the definition of differentiability, and we'll have to show that G satisfies the definition of differentiability with this object as its Jacobian. I want to just remind you of these Lipschitz bounds that we talked about last time, because they'll matter today. So let me just remind you of this. All right, so if f is continuously differentiable and non-singular, rather the Jacobian is non-singular, on an open set U, okay, so we have this thing well behaved on a set that takes up space. And now we pick a compact set within this. Right? Once we start trying to find like hard bounds or maximas on things, you need to work on closed sets typically. Okay, so N is closed. Then we can find these constants. I'll call them C and M. And they're positive constants. Okay, and these constants are going to relate to the norm of the Jacobian and the norm of the inverse Jacobian. Okay, and what will these do for us? We'll be able to say that if we look at f of v minus f of w and take its length, well, that we can relate to the distance between v and w itself through these constants. So this is going to be less than or equal to m times the length of v minus w. All right, so this is kind of our usual Lipschitz bound. And m is going to be related to the Jacobian, the norm of the Jacobian of f somewhere. But then we said we could also do this in reverse. This was a statement that, well, we wanted to know if the f's are close together, does that mean v and w are close together? And we said it probably relates to kind of how flat things are locally. You know, if the derivative is close to 0, then it's not so good. If the Jacobian isn't invertible at all, then it's really not good. And in general, as long as the Jacobian is invertible, we can find this constant such that we can say this. Okay, so let us just keep this in the back of our mind. Unfortunately, I have a small whiteboard here, so all the important things that I want to leave up through the whole proof are probably not going to stay up through the whole proof. But this we're certainly going to keep using. All right, so are we happy with a plan of attack here? So I'm going to start with this guy. I'm going to write down the lemma. I think I'm going to draw a little picture to go along with the lemma. And I'm going to probably try not to erase this picture as we go, because we'll try to use the picture to remind ourselves what's going on. Okay, so here is my first lemma. Let's let U be an open set. Okay, with f continuously differentiable, our usual hypotheses. Okay, and the Jacobian is invertible. Okay, so this is just a generic open set, okay? In particular, it will apply to this open set here that we identify later on. And we're going to say then, f of u is also open. Okay, so we've got to come back to definitions here. We're going to have to work carefully with definitions today. So let's see what we're going to try to do here. We have over here our set U. Okay, U is open. And F is going to take this to some other set. All right, what's my goal? My goal is to prove that this is an open set. So how do I prove something's an open set? Yeah, Luke.
Show that every point's interior?
I show that every point's interior. Right, so I'm going to pick a generic point in this set. I'm going to call it y naught. I'm going to draw it close to the center here just to give myself room to work. But of course, this can be any point in this set. And our goal is going to show that this is an interior point. What does that mean? It means I need to be able to draw some kind of neighborhood around here that completely stays in the set. So that's our goal, is to construct some neighborhood around this point. Okay, so let's choose any y naught in this set. And we know what we're trying to do. We're trying to build a neighborhood around this. Okay, now we know something about this y naught, right? This point corresponds to something from out here. It came from out here somehow. Okay, I mean, I guess possibly we don't know that this is an invertible mapping at all. So maybe it came from multiple places, but it came from at least one place. Okay, so I'm not assuming this is unique, but it's certainly such a point exists. That's what it means for this to be in the image. Okay, so we know that there exists some x naught in our original set such that y naught equals f of x naught. This is an open set, right? We'd love to show that this is an open set. We do know that this is an open set. So at the very least, I can draw a neighborhood around this guy. Right? That's the definition of it being open. This is an interior point. Again, there may have been multiple x naughts that I could choose, I don't know, but any of them is an interior point. So I can certainly draw some ball around here that stays in the set. Okay, so U is open. So that means there exists some delta greater than 0 such that let me call this set N. N is my neighborhood here. N is going to be the ball of radius delta, and it's going to stay in the set U. Okay, and we can certainly take this small enough so that actually n bar stays in U. That's fine too, right? Because if it doesn't stay in U, I just half the radius or something. Okay, so we'll say and n bar stays in U. And why do I care about that? I care about that because I want closed sets so that I can have these estimates to work with here. Because we're going to care a lot about somehow using, these kind of estimates to turn my delta for this set into a delta for the next set. It's the typical thing we do when, one of our sets is our epsilon, one of our sets is our delta, and we need to relate them to each other somehow. These estimates tell us how distances from here translate to distances over here. Okay, so we have this C and this M. Okay, and there exists C greater than 0. That's the one we're, I think, really going to need here. Such that if W and V are in n bar, then f of W minus f of V is bigger than or equal to C times W minus V. Okay, now somehow we've got to construct a neighborhood. Okay, so I have this ball here. This ball that I've called N, that also is going to map somewhere here. It's going to map to somewhere that I can call f of n, which may not be a ball, right? It's just some collection of points. Okay, so let's call this my f of n. But I want to somehow use this to say I can draw a neighborhood that maybe stays in f of n. And if it stays in f of n, it stays in f of u. So what we're going to try to characterize a little bit is where do these points in the set n actually go? Where do they land? And what I'm going to hope is that they kind of land far enough away from y naught that I have enough space to build the ball here. That's what I really want to do. I want to be able to say that the points on the boundary here land far enough away that they kind of fill up space and I can still squeeze a ball in here. Okay, so that's what I want to argue first, is that if I take points on the boundary here, all right, they're not going to come and land right on top of y naught. They're going to try to kind of land far away from y naught. If I'm far away from x naught, we're going to try to land far away from y naught. Okay, so what do we know here? We know that if x is on the boundary of n, okay, so what does that mean? That means x minus x naught is equal to delta. What do we have? Okay, so I want to know where this point lands, where this x here lands relative to y naught. So I'm going to look at f of x minus y naught and see how big that is. Okay, and again, it's this estimate that's going to let me do this, okay? Because I'm actually comparing two f values here, right? Y naught was f of x naught. So this is really f of x minus f of x naught, right? X naught lives in my set n. X lives on the boundary of n. It lives in n bar, okay? So this is valid here. Here I can say that this is bigger than or equal to c times x minus x naught. Which is c delta. Okay, so what happens here? If I took my x here and it landed, say, somewhere out here, then this distance between them is at least c delta. Maybe more, but at least c delta. Okay, so, and if I took a different point, again, it would be at least C delta. So I'm going to just find some new delta prime, say, that's a little bit less than this, okay, such that we're always at least a distance delta away. Okay, so let me draw a slightly smaller delta prime. Okay, and boundary points are always going to be mapped farther away than delta prime. So we're going to say this is equal to some delta prime. And say we take, just to pick something, it doesn't matter so much what we pick. So we pick delta prime equal half C delta. Just to pick something. I could take any fraction that I wanted. Now this is what I propose. I'm going to propose to argue that if we take a ball of this radius, an open ball of this radius, that it's going to completely stay inside of f of n, which completely stays inside of f of u. Yes?
What are the boundaries? Is that f of x now or f of x?
Ah, that's f of x. Thank you. Okay, so boundary points move this distance away, C delta potentially. Now, as long as I take something a little bit smaller than C delta, I've picked half here, it doesn't matter. As long as I take something a little bit smaller, I'm going to argue that this ball of radius delta prime, okay, so this is a ball of radius delta prime, I'm going to argue that that stays inside of f of n, which then stays inside of f of u. So this is my goal. So this is what I propose to show. Let's show that this ball centered at y0 of radius delta prime completely stays inside of f of n. Yeah, we certainly know that points in this ball are closer to y0 than the boundary points of n get mapped to. Okay. Now, we don't know yet that some bizarre reshuffling of points hasn't happened so that boundary points get mapped far away and other points get mapped even farther away. That could happen if we have a weird mapping. So we have to worry about that. But this, you know, from the picture that we're drawing here is maybe a reasonable thing to try. Okay, so once again, I'm trying to show that this ball stays in this set. That means if I take any generic point in this ball, I need to show that it stays in this set. Okay, so we started with y0, just a generic point in f of u. Now I'm going to take another generic point y. So let's choose any y in this neighborhood. Okay, so now I've picked some generic y. So our goal is to show that y belongs to f of n. Are we happy with this as a goal? Okay. What does it mean for y to belong to f of n?
X is in the neighborhood.
The x lives in the neighborhood, right? So we know that this y comes from somewhere, right? Comes from somewhere in u. Right now, that's all I know. Maybe it came from over here. Right? But it came from somewhere. That's the definition of the image. What I want to show is actually it came from somewhere inside of this set n. So there's somewhere out here, there's an x star that y came from. We want to know where it is. We want to identify it as having been inside this neighborhood. Right. So again, every step is a bit technical here, but we're just coming down to the simple definitions. We're stringing a lot of them together in ways that are less simple. But at every step here, we're just trying to build on the basic things that we know. So we know there exists some x star such that y equals f of x star, and x star belongs to u. And we hope that actually there exists an x star in n such that y equals f of x star. So I'm going to look at, okay, everywhere in this ball, probably everywhere on the closure of the ball, I'm going to look at the values of f of x I get. Where do these go? And I'm going to hope that one of them is equal to y. Another way of saying that is I'm going to look at y minus f of x, and I'm going to see how that varies over this ball, and I'm going to hope that I can make it vanish. I think we have used this trick before in much simpler settings, maybe with proving Cauchy-Schwarz or something. So we're going to do it in a little more sophisticated setting, but let's look at this guy. Oops. E of x equals f of x minus y squared. Okay? And we're going to look at what this does on the compact set n bar. Right, at the end of the day, I don't really care what this does outside of n. Again, y could have come from multiple points. I'm not claiming at this stage we have an invertible function. But what I'm hoping is that I can make this vanish somewhere. So this is the question we want to ask. Does E vanish somewhere on n bar? If it vanishes, then we're done, right? If we can find one point where it vanishes on this set, and we can argue that it's actually an interior point, that's important too, then we'd be done. Then we would have shown that our x star lives in this set somewhere. So this is what we're hoping. I want to know if it vanishes. So what I'm going to try to do is say, well, is there a look at the minimum of this thing. Try to argue that there is a minimum. There is a minimum because this is a continuous function on a compact set. So there is an actual minimum, right? And then we want to argue that actually the minimum is 0. Yes? We're okay? Okay, so let's try to argue that this minimum is 0. So E is continuous. And n bar is compact. So there is a minimum. Now what I want to argue again is two things. One is that the minimum is 0, but two is that the minimum is in the interior, not on the boundary. Because I really want this to land inside the open set n. I need to be able to construct and n originally was an open set, so that's where I really need it to live, not on the boundary. Okay, so I'm going to first ask what does this do on the boundary? What does E do on the boundary of n? And then we'll ask what does it do on the interior of n? And we're going to hope that the interior gives us a smaller value than the boundary. So first possibility is if x is a boundary point, all right, so let's see what we know. We've kind of written down things like this before. Okay, so I'm going to compare I'm trying to compare y to f of x, and I'll kind of do it by means of this central point here, why not? Okay, so and I'm going to use, so I actually want my inequalities to go this way. What I want to do is actually show that on the boundary, this difference is quite large, and that I can certainly make it smaller in the interior. So I definitely want inequalities going this direction. We're going to say, this is big. We're going to do better by moving to the interior. Okay, so f of x minus y, if I use my reverse triangle inequality, minus y naught. Okay, f of x minus y naught. So x is one of these boundary points here, okay, that got mapped out here, a distance at least c delta away. Yes? Okay, so f of x minus y naught, this is why I'm comparing to y naught, because all the estimates I had before were comparing to y naught. F of x minus y naught is pretty big. It's at least c delta. What about y? Well, y is living inside this little ball that I drew here, ball of radius delta prime. So y minus y naught, this distance is less than delta prime. Okay, so this distance is less than delta prime. Since there's a minus sign there, that's the right direction. So we'll call this delta prime. And delta prime, we chose to be less than this. I define it to be half of this, just to pick something. So this is going to be 1/2 c delta. Okay, so let's see. This was 1/2 c delta, which was also, I guess, delta prime. You can call it whichever you like. I'll write them both there, and then we'll decide later what pops up. Okay, so if I look at my e of x, what is my e of x going to be? On the boundary, e of x is going to be bigger than delta prime squared. Now, on the other hand, I could compare other points in here. I want to show that that's too big, that I can do better by looking to the interior. So right now, I don't have to identify the exact point where the minimum is. I just have to show that somewhere in the interior here, I can do better. All right? If I found one point in the interior that gives me a lesser value, then I know that the minimum is not on the boundary. It's somewhere in the interior. Maybe not at the point I picked to look at, but somewhere. So what's a good point to look at? Okay, so we looked at what happened on the boundary here. We've got some bounds here. What would be a good interior point in N to pick, just to try out? Yeah. Yeah, y naught or x naught, I guess. Yeah. I was pointing to that picture while I was talking, but indeed E is defined on x. So what I want to do is show that E of x naught gives me a smaller value than that. Okay? It doesn't mean that x naught is the minimizer. It just means that this is certainly not the minimizer, right? Okay, so let's see what E of x naught gives me. So E of x naught is going to be equal to f of x naught minus y squared. That's y minus y naught squared. All right, y minus y naught, well, y lives inside this little ball. All right, so that distance is less than delta prime. So this is less than delta prime squared. Okay, so I've plugged two different points into my function e, got two different values. One of them is strictly bigger than the other one. So this guy is not the minimizer. This guy may be the minimizer, it might not be the minimizer, I don't know. But this guy is certainly not the minimizer. All right, so if x is on the boundary, x does not minimize e. Okay, but we know there's a minimum. Somewhere on the closure of this ball, there's a minimum. It doesn't happen on the boundary, so it must be an interior minimum. Okay, so E has a minimum in the interior of N. This is kind of good news. I mean, first of all, obviously we want to show it vanishes. The minimum had better be in the interior because we're trying to show that it vanishes inside the open set. But secondly, we have more tools up our sleeve for how to characterize an interior minimum. Okay, I have a nice, pretty simple function here. It's quadratic, right? Obviously it takes vectors in, but it's quadratic. And now we know it has a minimum somewhere. So what is true at the minimum?
For every x there, the e of x is less than or equal.
Right, so that will be, the x there will be, the e will be less than or equal to anywhere else. What else is true of an interior minimum?
E of x should be 0.
Gradient of e of x should be 0. Right, we don't know that the minimum, we don't know yet that the minimum is 0. We hope it is. But, right, this is a nice differentiable function. Actually, this is, if you're going into optimization or anything where you're minimizing, this is going to be your favorite function in the world to minimize because it's just a beautiful quadratic convex function. And we know that at the minimum, the gradient is 0, right? First year calculus. Okay, so this is our function, which is quadratic. I'm about to erase it. Okay, so that means there exists some x star belonging to n, belonging to the interior, such that the gradient of e at x star is equal to the 0 vector. The good news is this was a simple quadratic function, which means I can write down its gradient explicitly. Okay, so let's do our usual chain rule here. Okay, so I'm going to have, here's the Jacobian of my inner function. The 2 came down and I had f of x minus y.
That line in a little more detail.
So this is your usual chain rule, right? We differentiate, what you expect when you differentiate a quadratic is 2 times f of x minus y times the gradient of f. These are, when you start taking Jacobians, right? These are matrices, and you got to get the size right because left multiplication, right multiplication, these are different things. And it's a fairly simple check, but not super interesting. You can do this component-wise if you want to convince yourself this is true. Okay. And just, literally go through E, take its derivative with take its different partial derivatives and convince yourself that this is the matrix vector multiplication that gives you the result.
Or you can expand this if you want to say.
You can expand it, exactly.
Because the square is the quantity times the quantity transport.
Yeah. So what's important here is this is an invertible matrix. right? That was one of our assumptions. The Jacobian is invertible. Since the Jacobian is invertible, okay, that means its transpose is also invertible. That means that actually, okay, so this is invertible matrix times some vector equals 0. If this is an invertible matrix, if A is an invertible matrix, what is the solution of AX equals 0? 0, right? This is an invertible matrix, so this times a vector equals 0 has only the trivial solution. Okay? So that means actually f of x star minus y is necessarily 0. That's the only solution we have to this. And that's what pretty much what we wanted to find here. We found that, all right, this point y came from some x star, right? And now we know actually that x star lives inside my set n. So this y here came from some x star over here, which we've now identified as living in the set n. And y is now equal to f of x star. We know that for sure. Okay, so in other words, there exists some x star in n such that y equals f of x star. Okay, so what did that mean? That meant we picked a generic y over here, right? And we've shown that whichever y we picked in this ball had to come from this ball n. Okay, so we know that. Where did this y come from? This y came from the ball of radius delta prime around y naught. And no matter what point I think I called this B, the ball. No matter what point we pick in this ball, or generic point y, we always found that actually it came from our set f of n. I could always trace it back to a point in my original set n. And of course, the image of the set n is certainly contained in the image of the u, because n is contained in u. So this means what? This means that this guy was an interior point, right? That's the definition of an interior point that we've been chasing. So y naught is an interior point. And again, there was absolutely nothing special about y naught. Y naught was just a generic point in this set, which I drew in the middle of the set just to give me room to draw lots of big neighborhoods around it. But I could have drawn it absolutely anywhere in here that you like. That doesn't matter. So this indeed tells us that since y naught was a generic point, indeed f of u is an open set. Questions? So this is a big proof. I didn't do any magic here, but I strung together a lot of different things. Probably this is about the hardest thing that we're going to see this semester. If you're getting worried, we don't continually ramp up in difficulty. But it's important to see where this came from, and this is going to be the hardest part about proving the inverse function theorem. This silly little technical detail, which actually matters a lot. Are there any questions on here? I feel like I need to give you guys a minute to just take a breath.
I'm gonna have to read it through again.
Yeah, I don't expect you to, be able to sit down and write out the whole proof from scratch on your own immediately after class. But it's a good exercise in seeing how these simple definitions that we've been building up the last few weeks, we can string them together into quite a sophisticated result. And again, I don't think I did any real magic here. So, I didn't introduce any new concepts, I think, in this, or any really big tricks, but it's a lot of ideas strung together. You're still drawing the picture. I won't erase it. The picture, of course, doesn't prove anything, but I think it helps a lot with trying to keep track of what in the world we're trying to do here. So let's go from there into trying to argue, actually, we've got local invertibility. The good news is there's not much left to do on this. All right, so let f be continuously differentiable. Okay, all our usual hypotheses. There's nothing new here. Okay, on an open set S. With the Jacobian invertible. Okay, we know we don't expect this mapping to be invertible. And nowhere in the last proof did I use the fact that it could be invertible. Okay, but we're going to say that if we pick a point in the set, it should be locally invertible. So then there exists some neighborhood we have some neighborhood n of x naught on which f is invertible. So we pretty much already have the proof. We've written down really all the steps of it already, so I'll just remind you of a couple important lines. I'm going to propose this as my n. Okay, so we had some nice, well-behaved, some nice delta where we could draw this nice ball here. So let's use our same n. Okay, and we said there is some positive C such that if U and V are in this set, right? And we said it was true for the closure of the set, but it's also true for U and V in the open set, right? Then f of U minus f of V is bigger than or equal to C times the length of U minus V. Okay, in particular, what are we interested in? We're interested in asking is f invertible? So is f invertible, the question of is f invertible is if I put in two different inputs, I should get two different outputs, right? The two different inputs here shouldn't all collapse to the same point here. Well, if U is not equal to V, then this estimate gives us actually that this is bigger than 0, right? The only way U minus V is 0 is if U is equal to V. And that in turn means that f of U is not f of V. And that's the statement of invertibility. F is invertible on n. And that kind of fits with our picture from 1D, right? Our picture from 1D, nothing bad happened unless the derivative became 0, became flat. right? If the derivative became flat, that would correspond to this c becoming 0, and we'd kind of get no information here. But as long as we've got an actual non-zero derivative, an actual invertible Jacobian everywhere, as 2 points move away from each other, the function values, which are locally linear, right, are also going to move away from each other, as long as we're on a small enough neighborhood. So we have invertibility. That guy's okay?
Yes, about the inequality.
Yeah.
The set on which these vectors lie should be open or closed.
On which these vectors lie. So this holds for n bar. So the lemma, these Lipschitz lemmas said that, all right, we've got an open set where everything is nice. Within that, we can find a closed set on which we have these inequalities. Okay, a closed set that takes a volume on which we have these inequalities. So but if this holds on the closed set, then it automatically also holds on the interior of that closed set. But yeah, the lemmas on these Lipschitz bounds stated this for a closed set.
What if u and v are in the boundary?
Then this will still hold if u and v are on the boundary. Right, so I guess our statement about invertibility said we can find a neighborhood. By definition, a neighborhood is an open set on which this holds. Yes, you can extend it up to the boundary too then, as long as the boundary is still inside your original set U. But I guess we've defined n to be in there. So yes, this would hold up to the boundary. All right, then let's do the last piece is the Jacobians. All right, so let F, okay, our usual assumptions. Let F be regular on an open set S. Okay, so now I'm going to assume the things that we've just proved. Okay, we now have an invertible function, right, which is invertible on this little neighborhood at least. Let F be regular on an open set. Okay, we define this local inverse on S. And then we can say that G is differentiable on its domain. Its domain is f of S. And we have an expression for its Jacobian. Okay, so what do we have here? Here's our set S, whatever it is. And let's pick our reference point. And this came from some other set that I'll call f of S. And X is correlated to some point Y. Now, okay, so S we assumed was an open set. F of S we now know is an open set because we went to a whole lot of work to prove that. So we know that f of S is open. I think this one can go now. So I'm going to start by arguing that G is continuous, and then I'm going to boost that up to differentiability. Okay, so let's choose any y. Okay, and let x equal g of y. Okay, g goes this direction. All right, so we know that when we're thinking about continuity and differentiability, we're going to look at our reference point and compare it to what happens nearby. Good news is everything nearby stays inside this set because it's an open set. Okay, so for any k in Rn, okay, so this is y. I'm going to call this y plus k. Okay, so k is that vector. Okay, with k small enough, we know that f of y plus k stays in our set, since f of s is open. Okay, so I can pick some length, right, such this ball stays in here, and all these different directions that we have to look at are in our set. And going from here to here is going to correspond to going from here to somewhere else. Okay, so I'll call this x plus h. Okay, so let's define h to be. Okay, so h is going to be the difference between this point and this point. So this point came from this guy here, y plus k, and then we took our inverse function of it. So g of y plus k minus g of y. All right, I like to see differences of the function like this floating around, because these are the kinds of things that are going to pop up when we talk about continuity, when we talk about differentiability. Okay, so we have this, and let's just kind of write down everything we can about relating them to each other. F of x plus h. All right, so f of x goes to y, f of x plus h is equal to y plus k. Which is the same as f of x plus k. All right, f is regular. It has all the nice properties. It has all the nice bounds that we just proved. Okay, so since this is true, let's write down those bounds. What is the key? The key is that we can relate this kind of length to this kind of length, right? This is, you know, if this length k is bounded, then it's going to also impose some bounds on h and vice versa, because we've got nice mappings here. So we know that there exists c greater than 0 such that c times h is less than or equal to f of x plus h minus f of x. Okay, these are the same kind of, you know, reverse Lipschitz bounds that we keep using. Now I've just, instead of f of u, f of v, or whatever, I've plugged in x plus h and x. Well, x plus h minus x is h. Okay, and this we said was equal to k. Okay, and I can also do it for my inverse function, g of y plus k minus g of y. which is, so I'm kind of just writing all the different permutations of these things, and then we'll see what we need. This is equal to h, and h here is less than the length of k divided by c. Okay, so right, in other words, I get some kind of Lipschitz bound for this inverse function now too. Okay, well, if I have a Lipschitz bound for this, I guess that says that if by taking k arbitrarily small, right, I can make this less than any epsilon. So this already is a statement that G is continuous. I mean, this is Lipschitz continuity, which is stronger than continuity. So here we have some kind of Lipschitz continuity. So we have continuity. So G is kind of nice. But now what I want to do is not just get continuity, I want to get differentiability, which we know is not the same thing. But these estimates will still be really useful in doing that, because when I write down the definition of differentiability, what's going to show up in there? Well, it's the difference between G at some point and G at my reference point, and then something that involves the Jacobian of G, right? So these kind of estimates will be useful. Then I'm going to want to translate all of this into the statement that f is differentiable, and that's going to make things like this pop up, okay? So that's why I'm kind of writing all of these bounds. I'm just putting down all the permutations of them I can think of here, and then we'll use what we need as we work through the particular limit that we know we need to evaluate. Okay, so we want to check the definition of differentiability. Okay, that particular limit that we have to check. Okay, with the Jacobian of G equals the Jacobian of f inverse. Okay, I'm going to check it at this particular point y. We're going to see if G is differentiable at this point y, which is just a generic point. Okay, and what does it require us to do? It requires us to look at all the nearby points and see what happens as they approach y. Or another way of saying this is, let's look at all these points of the form y plus k and take the length of k to 0. Okay, so I'm going to have G at this point minus G at this point minus stuff that involves the Jacobian. Okay, so this is the guy I'm going to want to take a limit of. Right? G at my nearby points minus G at y. Okay, then what did we have? We had something that involved the Jacobian of f inverse times y plus k minus y. So just k here. And then we had to divide this by y plus k minus y, so the length of k. Okay, and we know this is what we want to take a limit of. So our goal is to show that this limits to 0. So the limit as the length of k goes to 0, E of k is equal to 0. Right, that's the definition of differentiability. If I can show this is true, then G is differentiable, and we've identified this object as its Jacobian. So again, I'm not trying to do any magic here. I'm going to use what I know. What I know is that I started with a differentiable transformation f here. So there's another limit, very similar limit, that f satisfies. So what I really kind of want to do is just rearrange this, turn the g's into f's, and try to make this definition of differentiability pop out with f, and then we can say something. So that's what I'm going to try to do. I'm going to take these terms and try to turn everything into f's, and try to turn everything into f's and h's. All right, and we have, you know, a whole bunch of list of ways that these things are related to each other to help us go there. Okay, so let's look at the numerator first of all. Well, g of y plus k minus g of y minus the Jacobian inverse times k equals. All right, so what do I want? I want to get everything in terms of basically f's and h's. Okay, so let's see. G of y plus k minus g of y. Okay, that's written down over here. I called that h. Minus Jacobian of f inverse times k. I'll leave k here for one more step. All right, so I don't really want to have Jacobians of f inverse floating around too much. What I need is to insert a Jacobian of f in here somewhere. The easiest way maybe to do that is to say, well, I have a matrix here, matrix times a vector. I'm going to turn this into a matrix vector product too, the identity times h, right? So that I can have hope of trying to factor things. And I'm going to try to write the identity in a useful way as the inverse Jacobian times the Jacobian. That will let me factor this out, and then hopefully what's inside looks like the statement that f is differentiable. That's my goal. Pull this out, hope that everything left is what I want, and know that this is some well-behaved object because we have a nice regular mapping. Okay, so this is going to be Jacobian of f inverse that I factor out times the Jacobian of f itself times h minus k. All right, let us find k here. Here's a place that lets me relate my k's to my f's. If I rearrange this a little bit, k is equal to f of x plus h minus f of x. That would be good. And I'm going to pull a minus sign out because I have the feeling that that will give me exactly what I want. So k is f of x plus h minus f of x minus this Jacobian times h. That's starting to look very promising. This is the numerator in my definition of differentiability, right, times this other matrix. Okay, so let's come back to here and see if we can bound this by something that limits to 0. I think I can erase this picture. Okay, so let's see what we have here. We have E of k is less than or equal to okay, so I'm doing bounds. So this is, all right, a matrix times a vector. I can bound that when I'm bounding the magnitude by norm of this times length of this. Okay, so Jacobian of f inverse. Oh, sorry. Inverse. Put it there. Which is just a number, right? This is an invertible matrix. We're at a fixed location x, so this is just a number. All the rest of this stuff okay, divided by the length of k. Okay, so again, all right, this is just a constant number. This is the numerator. This is the right numerator. This is not the right denominator. I need an h in the denominator. But I have a whole list of how all these things are connected to each other. So let's see. It looks like the length of k is bigger than or equal to c times h. Okay, so this guy here, bigger than or equal to c times h. All right, he's in the denominator, so that's going to make this whole thing go Jacobian of f inverse times the numerator, don't want to change, I like it, divided by c times h. Okay, so the limit as k goes to 0 of this is bounded by the limit as k goes to the 0 of this. Now, I guess the last thing to check is that as k goes to 0, does h go to 0? So as k goes to 0, does h go to 0? It does. We have this bound that actually h is less than length of k over c. So the answer is yes, since, again, I'll call it this, h is less than or equal to the length of k over c. Okay, so taking the limit as k goes to 0 is equivalent to taking the limit as h goes to 0. So I'm going to be able to say at the end of the day that the limit as k goes to 0 of e of k in magnitude is bounded by, all right, this stuff that's just constants, times the limit as h goes to 0 of all of this, divided by the length of h. All right, again, these are just numbers. C we know is a positive constant because everything's regular. Jacobian of f inverse is just some matrix. X is a fixed point, right? So this is just a constant. It's not changing. So it's just a number, positive number. This limit we know goes to 0 because we know that f is differentiable. This is the statement that f is differentiable. So indeed we can say this is 0 since f is differentiable. And that was our goal. That was the object that here it is. That was exactly what we needed to show in order to prove that, yes, G is differentiable, and actually its Jacobian is just the inverse of our original Jacobian. So this is where we wanted to land. And that's the last piece of our inverse function theorem. Questions? Yeah.
So in order to show this, we had to use that the Jacobian of G was the inverse Jacobian of f, right?
Right, so we checked this limit. So the question is, did we have to use that Jacobian of G was inverse Jacobian of f? We had to hypothesize that. But this limit being 0 is precisely the statement that the Jacobian of G is equal to this object. But yes, we had to hypothesize what it should be. And we didn't guess wildly. We hypothesized that by using what we knew about linear transformations and saying, locally, this thing looks linear, so hopefully that information still holds. So we had a guess, but it was an educated guess. Yeah?
The norm of the Jacobian inverse of f.
Yes?
Is it always finite?
Is it always finite? Yes, this is finite because we've assumed that the Jacobian of f is invertible. And this is, the norm of this matrix is related to an eigenvalue problem where you're looking at the matrix times its transpose, something like that, and picking the largest eigenvalue. So you can check that, yes, this matrix norm will be always finite. Other questions? It's a big result. You know, we said that you can use this now to get really good approximations of your linearization, to use the linearization of your inverse mapping. This is what Newton's method does, actually. It says, you know, I want to solve f of x equals 0. I want to compute g of 0. I don't know it. Let me use the inverse function theorem, treat g locally as its linearization, and find out where that hits 0. That's exactly what Newton's method does. And then you get a new guess, and you try it again. You say, let me linearize my inverse mapping about this new point. So this is a big result that we'll prove once, and only once, but is tremendously useful. From here, we're going to go on to non-square mappings. What can we say about mappings where the number of inputs is different than the number of outputs? So there'll be kind of a similar flavor to it, but the good news is we've done the hardest work of proving that. So next class, we'll go back to intuition building for the non-square case and work our way up to the implicit function theorem.